Hello, you awesome young chemistry students. I want to walk you through, just real quick, a couple problems with calculating percent yield. If you are currently in my class, you will find that the questions I'm going to walk you through are questions 1 and questions 4 on the homework that's assigned. So you can go ahead and take a look at that and then have a better idea of how to do that. So then you have some examples to move on with the rest of the homework. So first of all, to calculate a percent yield, you take your actual divided by your theoretical yield. Now I want you to understand theoretical yields, they are figured out or obtained through the stoichiometry. So you're going to have to use like a problem to figure out, hey, in theory, if I ran this reaction, what would it produce? Actual yields are obtained experimentally. So you actually have to do the lab to figure out, hey, what do I actually form here? So just like thinking about actual yield divided by theoretical yield, think about if you get a test back. Say you get a 93 out of 100. So your actual yield, this is your score that you received. And in theory, in our class, you should have gotten 100, but you didn't, and a 93 is still great. So this is like the theoretical score, meaning how much it should be. And you guys know when you have a 93 out of 100 on your paper, for example, you divide 93 divided by 100 times 100, which obviously ends up being a 93. So that goes for any score that you would get upon your paper. So think of it that way. Your actual always goes on top, divided by your theoretical. So let's take a look at what these problems might look like. In the reaction of zinc with hydrochloric, in this particular reaction, we don't really need to write this reaction, but if we were thinking about this, it would be zinc with hydrochloric, and we're going to produce some hydrogen gas and zinc chloride. Again, this reaction is really not necessary in this equation or to find the theoretical field, because what we're given is 140.15 was actually formed. So here's our actual yield. And the stoichiometry is already done for us here. Although the theoretical yield was 143 grams. That's the theoretical yield. So we want to just simply find what's the percent yield. So we're just going to do a simple calculation. Percent yield equals our actual yield, which is 140.15 grams, divided by our theoretical yield, which is 143, times 100 just to get it into percent. So if I would go through and calculate that, I would get 98.0%. This right here is an excellent yield. Typically, we in real life don't get really close to 98% yields. Simple experiments is very difficult sometimes, especially in a high school lab. So honestly, anything that's over about a 70% is a very good yield. Even 50s or 60% are like fair and doable to get that yield. Anything below a 50%, I mean, you should do it all over again to try to get a much better yield. But just keep in mind 98% is an excellent yield. So what might have happened to the 2% that's not there? It could have been lost as hydrogen gas somewhere. It could have been, hey, it didn't react fully. It could have been we had a difficult when we weighed something on the balance. There's lots of things, especially in a high school chemistry lab, where there's some sources of error. Let's take a look at this problem. Now, this problem makes us actually calculate the theoretical yield first. So what we have here is a sample of 0.8 moles of phosphorus, and we react it with an excess of sulfur. Now, this excess of sulfur is like, great, we've got plenty of sulfur. We don't really need to use that in our equation. And we're going to form diphosphorus pentasulfide. So at the end of the reaction, this equation gives us the actual yield. So what we want to do is we have to figure out the theoretical yield. So we have to use stoichiometry to figure out the theoretical yield. And that piece of information we're given is 0.8 moles of phosphorus. So we have 0.8 moles of phosphorus, and we have our equation, and it's balanced, so we're ready to do stoichiometry. We're already in moles, so let's go ahead and do our mole ratio. So according to our equation, we have 2 moles of phosphorus. And for every 1 mole, because there's nothing in front of diphosphorus pentasulfide for every 1 mole of P2S5. And then we're going to go ahead and calculate, and this equation or this question even gave us the molar mass. It's going to make our life so much easier. So we have 1 mole of P2S5 is equivalent to 222.3 grams. And this is simply the molar mass of diphosphorus pentasulfide. So we're going to figure out theoretically how much should be produced, and we're going to compare that to how much actually was produced. So we'll take 0.8 times 222.3, and we're going to divide that by 2, and we're going to get 88.9 grams. This is right here our theoretical yield. Theoretical yield is calculated using stoichiometry. We have our actual yield from the problem above. So we're going to come down here and take our actual yield, 82.7 grams, divided by our theoretical yield, 88.9 grams. So 82.7 is what we've gotten, 88.9 grams is what we should have gotten. We're going to multiply by 100, and to calculate and figure that out, we have a 93.1% yield, which again is an excellent yield. So right there, percent yield, don't make this harder than what it is. If the only time you need to really do stoichiometry is if you need to go ahead and calculate the theoretical yield on your own. Other than that, just make sure you have a theoretical yield and an actual yield. Just divide, you're good to go. Okay, so you guys got this. Remember, ask me questions if necessary, and we'll rock and roll. Take care. Have a great night, guys.